Whenever we study about something, we will also analyze its properties. Why we want to study about the properties? These properties will act as shortcuts for solving problems. If we know some peculiar properties of an idea, we can use it as a shortcuts to solve complicated problems, or we can predict the mathematical manipulation. See, this is coming like this, so because of this property it will be equal to this, right? So this is where properties come to handy for us. So it is a weapon, or it is a shortcut to solve complicated problems. So in this video we are going to see what are the properties of the convolution sum, the concept of convolution sum having some properties, and what are those properties. That is what we are going to see in this video.
There are some properties for this convolution sum equation, and analyzing these properties will help us to solve the problems in an easy manner, or it is a trick. Actually, it provides us some trick to come to some sudden conclusions or solve problems very easily. So the first property is commutative property, and the commutative property is actually talking about order of the signals, signals in convolution operation. Okay, convolution operation. Okay, order of the signal in convolution operation. Property says that x1 of n convolution x2 of n is equal to x2 of n convolution x1 of n. For example, assume that we have a system whose impulse response or response is x2 of n, or is. Now if I am giving x1 of n as the input to the system and convolve these two, I will get c of n. Okay, let it be there. Now I have another system. For that, x1 of n is the impulse response of the system. Then if I give x2 of n as the input and convolve both of them together, then also we will get c of n in the output. So that means they are equal. So changing the position of x1 of n and x2 of n between each other does not change the result of convolution, right? x1 of n can be input and x2 of n can be impulse response. x2 of n can be input and x1 of n can be the impulse response. That does not change the convolution result. That is what the commutative property says. Now coming to the next property, that is known as the distributive property. So distributive property says that we have sum of two signals x2 of n and x3 of n, and if you convolve that some signal with another signal x1 of n, that is equal to convolving x1 of n with x2 of n, and then x1 of n with x3 of n, and then adding them together. So it is equal to convolving them individually and adding them together. So in a graphical way we can illustrate it like this. For example, we have an x1 of n, that is the input signal. We have a system whose impulse response is sum of two signals, that is x2 of n and x3 of n, and if you give x1 of n inside and convolving, you will get c of n, right? So this is fine, and this can be done in opposite way also because of the previous property, that is commutative property, right? So because of commutative property, we can change the order, right? So you can give x2 of n plus x3 of n as the input signal, and we can keep x1 of n as the impulse response of the system. Then also you will get the same c of n, right? And both of these are equal, and that is equal to splitting the entire system into parallel connections. So you can see x1 of n is the input, and it will go to first system whose impulse response is x2 of n, and it will be convolving there, and it will go to the second system also whose impulse response is x3 of n, and there also it will be convolved, and finally we will add them together. Let us say this is c1 of n and this is c2 of n, right? So if you add c1 of n and c2 of n, we will get c of n, right? So this is what the distributive property says. The associative property says that we have an already convolved signal, right? x1 of n and x2 of n are already convolved, okay? Already convolved signal, right? Already convolved signal. If you convolve that with xi of n, then that is equal to convolving x2 of n and x3 of n first, right? This is another already convolved signal. This is an already convolved signal, and you can convolve that with x of n, right? So this is what associative property says. So graphically it has so many meanings, so let us try to understand them one by one. So we can convolve x1 of n and x2 of n, and then you can convolve that with x3 of n, you will get c of n, right? Keep x2 of n, convolve x3 of n as the system's impulse response, and give x1 of n as the input. Then also you will get the c of n, which is the same c of n. And here you can cascade. You can also cascade the systems, right? And the first system's impulse response is x2 of n, and the second one's impulse response is x3 of n. If you give x1 of n as the input, the first result will be x1 convolved x2, right? Now I will give that as the input to the next system. In the output I will get x1 of n convolution x2 of n convolution x3 of n, right? So this is our c of n. So due to the commutative property, we can change the order of this cascading. Instead of x3 of n, you can put x2 of n here and x2 of n here, and you can give x1 of n as the input. The same result c of n we will obtain in this result. So the associative property help us to change the order in cascading the systems, and we can split the systems into different cascades or serial connections because of this property. So that is the basic idea of associative property. Now coming to the shift property, assume that we have two signals x1 of n and x2 of n, and its convolved output is c of n, right? If I shift one signal x1 of n by time m, that is n minus m, and convolving that with x2 of n, then I will get an output that is c into n minus m. Now assume that I am delaying x2 of n by an index of p, that is n minus p, then convolving with x1 of n, the result will also be shifted in the equal time index, right? Now if I have two signals x1 of n and x2 of n, both are shifted by some time index m and p, right? Both are shifted by m and p. Then in the output you can see that the output convolved signal will be shifted by c n minus m minus p, right? So otherwise we can write c n minus m plus p, the whole bracket, like this you can do. So this is the shift property. So the basic essence of this property is that whenever some shift happen in any one of the signal or both the signals, that will reflect in the output signal also, convolved output also, right? That shift will reflect in the output convolved signal also. That is the basic idea of this shift property. Now coming to convolution with an impulse. What happens if I convolve a signal with impulse signal? What happens if I convolve a signal with impulse signal? Actually we will get the original signal back. So what is the basic idea here? Actually I have a signal like this. Assume that this is the 0 index, and I have a signal like this, and the second signal is delta of n, that is our impulse. So the impulse is having value only at n is equal to 0. Now if I wanted to perform the operation x of m into del of n minus m, summation m varies from minus infinity to plus infinity, what happened is that I am multiplying the shifted impulses. I am multiplying the shifted and scaled impulse. What is the scaling factor? That is x of m. So shifted and scaled impulses, adding shifted and scaled impulses. We have heard this somewhere, where it is approximation of any signal x of n using impulses, right? So surely this is equal to x of n, which we have already discussed in the beginning of this video series, that is approximating a signal using impulse. What kind of impulse? Shifted and scaled impulses, right? So that is what is happening here. So convolution of any signal with impulse will result in the same signal. So this is an important result. Sometimes we will use it in solving problems. Coming to the next property, that is shifting property or sampling property. Not that this is not shifting property, this is shifting property. So shifting means knocking out a value from a position or sample the value from a position. So assume that we have a signal x of n. I am multiplying x of n with del of n minus a. So what happened? I have a signal like this and assume that this is a, right? So what is meant by del of n minus a? Del of n minus a is a shifted signal. So where it will be located? It will be located at the position a, right? So all the other values are 0. All the other values are 0. So I am actually plotting del of n minus a here. So del of n minus a will have a value of 1 only at the location a, right? It has a value 1 only at the location a. Now if I multiply that with any signal, right? If I multiply that with any signal, what happened? All the other values are 0 because of this impulse signal. All the other values will become 0 and I will get the value of the signal corresponding to the index a, right? Only this value will come out, right? So this value will come out from the signal x of n, because when we multiply, what happens? All zeros will multiply with the other samples in the original signal and they become 0, and only the sample located at a, that is x of a, and that is equal to multiplied with the del of n minus a. So only one sample will be come out. So that is why it is known as sampling or sifting. Sifting means knocking out. So this operation, that is multiplying x of n with del of n minus a and adding all of them together, will knock out a value which is located at a, right? It will knock out a value which is located at a. So from a discrete time signal x of n, if you want to knock out or if you want to take out one value at a particular location, what you have to do? You have to multiply that signal with a shifted impulse which is located at that particular location, and then you perform this operation. Then you will get that signal back. So shifting or sampling property will take out or knock out one single sample or one single value of the discrete time sequence, and it will give to you, right? So that is the basic idea of this shifting or sampling property. And finally, the width property. So width property is important. If I convolve two signals h of n and x of n, what will be the width of the output signal y of n? What will be the width of the output signal y of n? So it can be understood in this way. So here you can see the width of the signal is 2 and here the width of the signal is 1. Right? This is width of the signal 2 and this is width of the signal 1. So we know that width of the output will be W1 plus W2, which we have already studied when we are discussing convolution integral. So please keep in your mind that the width of the output will be the sum of the width of the inputs, right? So if you take, you can see 1, 2, 3. So the width of the output is actually 3, right? So this is, I am talking about width, right? So width W is equal to 3. So till this time I was talking about the width of the signal. Actually width means from two non-zero, the width between two non-zero signals is known as width of the signal, right? And now I am going to talk about something else, number of elements, right? So see how many values are there? Value 1, value 2 and value 3. There are 3 values. L1 is equal to 3 elements are there in this particular signal. And how many elements are there in the second signal? Here we have L2 is equal to 2 elements are there, right? Now if you see the output, you can see 1, 2, 3 and 4 elements are there. So L is equal to 4. Can you find any relation? Yes, we can see that L is equal to L1 plus L2 minus 1, which is equal to 3 plus 2 minus 1, which is equal to 4. So 4 number of elements are there in the output. So what is the relation between width? The total width of the output will be equal to width 1 plus width 2, but total number of elements in the output will be equal to L1 plus L2 minus 1. So this is the relation. This is an important relation. In the convolved result, if the length of the first signal is L1 and the length of the second signal is L2, then the length of the output signal will be equal to L1 plus L2 minus 1. You have to keep this in your mind, right?
I hope you got a clear idea about the properties of convolution sum and it will be useful in solving different problems we face in the subject signals and systems.